Hello again, my dear students, and welcome back to our final lecture dealing with the advanced technology of the field effect transistors or the FETs. As I mentioned, maybe in the beginning of this course, I usually utilize the final lecture in order to demonstrate new technology related to the semiconductor devices. Herein, I promoted three advanced technology related to the field effect transistor in order to be demonstrated in this lecture. In this lecture, we are going to demonstrate what we or what is known by literature by the tunneling field effect transistor or the TFET and the thin field effect transistor or the TFT in its both forms, either in the inorganic form and or in the organic form, which is well known by the word OFETs. These are, from my perspective, three of the most famous booming and promising technologies related to the field effect transistor. So please permit me now to start sharing my presentation slides and to start this final journey with the advanced technologies related to the FET technology. Okay, so this lecture, which is our final lecture, deals with advanced field effect transistors, or what's called the FET technology. Maybe the first question comes to your mind, why we should change our standard MOSFET. We already have a MOSFET, and it's a well-known and very good operating. But why should we search for another technology? Maybe there is more than one reason to search for a more or advanced technology with respect to MOSFET. But from my perspective, the main reason is related to the dimension. If you remember, maybe in your first lecture in this course, or maybe in other courses, we have studied together what's known by the Moore's law, seeking for more number of transistors per unit area. And in order to implement more number of transistors per unit area, that means that you should scale down your transistor, which scaling down the channel lengths as well as all other parameters. Herein, fabricators starts to have some sort of obstacle whenever they narrow down or scale down the MOSFET in the sub micrometer range or typically in the nanometer scale. Accordingly, they start to think about having new or updated structures. Herein, when we are focusing on the word updated structures, we are referring on two parameters. Either to change the material, usually we are using silicon as a main semiconductor material in fabrication. So maybe the first stage is to search for another material. For example, here we are using indium arsenide. We have gallium arsenide, we have indium gallium phosphide, we have what's called IGZO. We will talk about it later on in this lecture and all other materials. So the first perspective is to change the material. And the second is to change the structure. So to have to introduce a new structure, like for example, TFT. Herein, this demonstration is implemented by Intel when they fabricated a tunneling field effect transistor with indium arsenide, and they found that this transistor is is 8 times faster than the standard MOSFET transistor. So this is the challenge. This is the target. We are seeking for a smaller transistors, higher number of transistors per unit area, more processing, as well as a faster transistor in terms of delay. As you can see here, delay is approximately 3%. So one of these technologies may be the tunneling field effect transistor, which is, we can think about it as what we call a PIN structure. And I'm not sure if you hear about this junction before, which is a PIN, but following our background in this module, I think you can think about it in a very good manner. We already have studied together what's called the PN junction, which is the normal die. And we see together these PN junctions in more than one format. Herein, we introduce an intrinsic layer in between a two doped layer. One is PN, one is N. This is what's called a PIN. Maybe some of you who have worked in projects related to the PIN junctions in your project module, maybe they hear about it. So the question will be now, what is the correlation between having a PIN junction and between what we call the tunneling effect? This is what we are trying to do in the first part of this lecture. So this is a very useful comparison between the standard MOSFET and what we are introducing now as a tunneling field effect transistor. Again, all these slides are captured from Intel. So MOSFETs have a source and drain and substrate. Usually, the substrate is in the alternative doping with respect to the source and drain. So if we have an N plus source and drain, then you have a P substrate. And this is what is represented by an N-channel MOSFET. Here we have the gate oxide and the gate, and this is a three-terminal device as we already studied. But and actually, this is the energy band diagram corresponding to this structure. So it's an NPN energy band diagram, as you can see. Okay, but now, what if I will keep the gate as it is, but I will turn the polarity or the doping, I mean, of one of the source and drain. So for example, here, the source is turned to be P, while the drain is kept as N. And then the substrate will be turned to be intrinsic. So if you examine now the junction you are examining here, let's make out the line. So this will be your junction. It's an PI and junction. P is the source, I is the substrate, the intrinsic substrate, and N is the drain. So now we turn the junction from being a PIN junction, from being a NPN junction to be a PIN junction. But the question is, what is the benefit from having such an energy band diagram? This is an N-type region. This is a P-type region. What is in between is an intrinsic. So how such a device will work? Let's see. So this is a PIN junction. But before proceeding, we already know that we have two types of junction. We have what's called the homo junction and what's called the hetero junction. If you remember, we have already studied this together in the metal semiconductor interfaces, whenever we studied the difference between a homo PN junction and a hetero PN junction, if you like. So an homo junction means that the three materials or the junction materials in general are implemented of the same material. So for example, the graph on the left, you can see that silicon is everywhere here in the P and the I and then that. However, whenever you introduce a new material to your structure, then you create what's called a hetero junction structure. Okay, so let's go. This is the first TFT implemented. It is implemented, I believe, in the UC Berkeley. Yes, in UC Berkeley. So this was implemented in 2018, and this was examined by the guys there, where they can fabricate it and they can characterize it using this standard TFT structure. Also, there is another schematic demonstrated some bit earlier by the Intel group here. It's a very sophisticated structure, as you can see. It's implemented on a semi-insulating substrate of indium phosphide, and then you have your structure as a PIN structure. So this is the N region, this is the I region, and this is the P region, as you can see. So it's N PI junction or PIN junction. You can demonstrate it. However, we have a set of materials with different properties and with different actually job description maybe in the structure. So, and this is also a fabricated structure. And herein maybe you can ask a very important question: why we are not considering this structure as a part of our analytical modeling? I mean, whenever you are dealing with the PN junction, with the MOSFETs, with the BGTs, you can have what's called a closed form or an analytical equation, mathematical equation that can describe the IV characteristics, for example. However, in this lecture, for example, we did not demonstrate any equation up till now. This is simply because, if you remember, the constraints or the boundaries of the drift diffusion model. This was demonstrated, I believe, in lecture number 1, in the revision lecture, when we say that this drift diffusion model is valid whenever the structure is in a dimension above the, let's say, 100 micrometer dimension, or of 10 or tens of micrometer dimension. Whenever you use devices scaled down to be in the nanometer range, no longer drift diffusion model can be used. That's why this types of structure, either the TFTs or the tunneling field of transistor, the thin film effect transistor, the organic filters, all these stuff cannot be demonstrated using the drift diffusion model. And accordingly, we need what's called the atomistic structure modeling or the quantum modeling in order to demonstrate such sophisticated structures. That's why, of course, this is out of scope of this module, and maybe this is somehow considered as an advanced topic in some postgraduate modules. But this is just to demonstrate why we are not using the standard diffusion model in demonstrating this. Okay, so instead of using mathematical equations, we are going to use some sort of conceptual demonstration. So this is our PIN structure. So as you can see, this is an N region, this is an intrinsic region, and this is a P region, for example, or the vice versa. So this is P, I'm sorry, this is N, and this is sorry, this is P, this is I, and this is N. It's PIN. So this is the energy diagram at the let's say at the thermodynamic equilibrium condition. So whenever the gate voltage is equal to 0, then your drain current is equal to 0. You don't have a current. You don't have a current flow. So if the gate 0, the drain current is equal to 0. What happens if we increase the gate voltage? So which is to be above the gate, to be above the threshold voltage. Simply what will happen that this channel will be narrowed down somehow, and accordingly you can see that. Let's now start to plot a line just to demonstrate the idea. Okay, so let me put this one. So if you examine this horizontal line, you will find that the valency band of the p-type material is now horizontally aligned to the conduction band of the n-type material. And there is only a small gap, which is the channel. Now, as you can see, the effect of the drain of the gate voltage is that it's narrowed down the channel. So in the first stage, which is the thermodynamic equilibrium stage, the channel was relatively wide. However, by applying this relatively high gate voltage, which is above the threshold voltage, the channel starts to be narrowed down. Accordingly, what will happen, my dear students, is that electrons can tunnel from the valency band of the p-type material to the conduction band of the n-type material due to the high applied electrical field or voltage on the drain. So electron tunnel this region and go directly to the conduction band of the n-type material. Whenever you have a flowing electron, then you have a current. This is the concept of the tunneling in the TFTs or in the tunneling field effect transistors. This is one of the interesting quantum effects. Again, this effect cannot be expressed by a semi-classical theory. You have to use a quantum model in order to demonstrate such an effect in a mathematical way, which is again out of scope of our module. So this is how tunneling works. So whenever electrons have a high electrical field, attraction force from the drain, and the gate voltage narrow down the channel. As you can see, the comparison between the left-hand side schematic and the right-hand side schematic, then electrons will start to tunnel from the source to the drain, and you will have current. Accordingly, we can have a characteristic curves to demonstrate the properties of this tunneling field effect transistor, and also maybe as you did in your projects on some devices, what we are going to do now is just to optimize the device. So for example, here, this optimization is in terms of the gate length. So they are changing the gate length and they see the effect of the transistor at different gate lengths. Here we can express the effect. And also maybe here we have a different characteristics by different materials, I think, and also by different, let me say, what is the variable here? Yeah, this is a single gate multiplied. I'm sorry, that's just the bar of the zoom height. That's the title of the page. So it's a single gate versus double gate. And by the way, sorry, multi-gate field effect transistors are also one of the very interesting structures that most of the fabricators, I mean Intel and IBM and all these stuff, starts to use whenever they narrow down the transistors or the MOSFET scale. Double gate and multi-gate transistors and thin gates are, all these stuffs are very interesting for in the semiconductor devices technology. Here another view for the transistor characteristics. Here we are varying the VDS. Of course, the VDS has a very important role in the characteristics because simply the gate voltage acts just to narrow down the channel. But the main reason for the tunneling is to have a drain voltage. Again, if you remember maybe the classical theory of MOSFET, the drain voltage is the voltage used to attract the electron from the source. So if you have a gate voltage but you don't have a drain voltage, then no current or no electrons will flow from the source to the drain. Similarly here, the gate voltage is act just to narrow down the channel. But the main reason for the electron to tunnel is to have an attraction force, a high electrical field coming from the drain. This is can be demonstrated in this graph. So the higher the drain voltage, the higher the current you have. Okay, so this is simply the story. And of course, as usual, I believe you used to see this slide in any lecture, which is the capacitance effect. Again, in any MOSFET, in any transistor, we have, or maybe in any semiconductor device, we have what we call the parasitic capacitance effect. And by the way, the parasitic capacitance effect is an extremely important parameter in calculating what we have demonstrated in the first slide, which is the delay. Because simply delays comes from charging and discharging, which is the capacitor role. Whenever you have a capacitor, then you have a charging time and discharging time, and this is a main factor in the delay. I believe that delay will become a very important parameter whenever you start your next course or your next module, next semester, inshallah, with the VLSI or the very large scale integrated circuit. So capacitance is very important, and that's why we are using, or we should demonstrate capacitance whenever we have a semiconductor device. And here in TFT's capacitance are also of interest for fabricators whenever they are fabricating tunneling field effect transistor. Okay, let's turn to another technology, which is what we call the thin film technology, the thin film transistor. The thin film transistors, or maybe it's more wide, what we are talking about what's called the thin film technology, is a very interesting technology where we have that set of devices that's working based on this thin film technology. So thin film transistors can be classified in two manners. The first is concerning to the material, the semiconductor material you are using. So again, it's a source and drain. We have an insulator here, and we have a gate electrode. So one of the interesting structures here is that we have what we call the bottom gate configuration. I will demonstrate different configuration later on in the next slide, but this is what we call a bottom gate structure. That's why you have the gate in the bottom and the source and drain in the front contact. So herein the semiconductor material, which is something in the dark red, as you can see, can be either an inorganic semiconductor material, which is this case, where we call this an inorganic TFT, or it can be an organic semiconductor material, where we call this an OFET, or organic field effect transistor. Okay, so here we can have also a different schematics. These are the four different configurations. We are usually classifying the configuration based on both aspects, the gate position and the contact position. So this is, for example, it's called a bottom gate top contact configuration. That's because the gate is in the bottom, as you can see, and the contact, which is the source and drain, are in the top. Here we have a bottom gate, bottom contact, all in the bottom. Here we have a top gate, bottom contact, the gate in the top and the contact in the bottom. And finally, we have a top gate, top contact, which is everything in the top. So you can demonstrate different structures of these TFTs based on the contact and the gate. Actually, it is always a debate which of these configurations is the best. And I can say that there is nothing called best. It depends on
a set of parameters. It depends on your application. It depends on your materials and it depends on your fabrication procedures. So maybe if you go to the literature, you will find that sometimes we are we are going to promote the bottom gate subconductor, for example, as a best, but in other applications you can have a different or another answers. So as I mentioned, okay, whenever we are going to demonstrate or we are going to evaluate, because I just mentioned in the previous slide that which transistor is the best. So what is the definition of the best? Whenever we are going to demonstrate the performance of any TFTs or any transistor in general, there are four main parameters that can evaluate the performance of a transistor. These parameters are the field effect mobility, the on-current ratio, the on-off current ratio, the subthreshold swing, and the threshold voltage. I believe you are quite sure you know what is the threshold voltage, which is the minimum voltage of the gate that makes the transistor turn on. The subthreshold swing is actually demonstrated in a very quick manner when we study together what's called the subthreshold voltage or the subthreshold current. If you return back to the MOSFET lecture, you will find an equation for the subthreshold swing. The on-off current ratio is very simple. It is related to the on current ratio is simply the saturation current. Whenever you have a transistor is on and is the saturation, theoretically it should have a constant current. But what about the off current? The off current is simply the current when the transistor is off. But the question is, do we have a current when the transistor is off? The answer is yes, because if you return back to the subthreshold swing, you will find that in the subthreshold region, the current is very, very small. If you remember, I show you the y-axis of the curve, and I said there is a current, but this current is a very, very small, maybe in the pico or the femtoampere. So there is a current. So the higher this ratio, the higher the amplifier. Theoretically speaking, this off current should be equals to zero, which means that this on-off current should be equals to infinity. But again, this is something hypothetical. Maybe the field effect mobility is something related to the mobility of the carrier to transfer from the source to the drain, and it can be found as an output of the differentiation between the log scale current and the voltage. This is somehow advanced for your study, so just recognize the term, and that's all. Maybe if you need this term later on, maybe in your graduation study or a graduation project, I mean, or maybe in your postgraduate or in your next career as an electronic designer, you can read more about this parameter. So these are the four parameters used to demonstrate or to evaluate the performance of this MOSFET. But now, let's go to the next. What about the materials? As I mentioned earlier, we have two models. We have what's called the inorganic semiconductor and the organic semiconductor. For the inorganic semiconductor, actually, the most famous material used is what's called the IGZO material, which is the indium gallium zinc oxide. What is interesting is it wasn't somehow adaptable to use silicon in the fabrication of TFTs. That's why you will not find a lot about silicon TFTs. However, IGZO is considered as the most famous material used in the fabrication. By the way, this result is our result. Is a result demonstrated by one of our genius students as a senior graduate student. She is doing her graduation project in organic versus inorganic TFTs. So this is our result, and I have to, of course, appreciate her intelligent and her smart structures, which results up with this very impressive results. So this is the most famous material, which is IGZO. IGZO used in various applications. Maybe we already deal with such applications. For example, this in our mobile phones, I believe all our mobile phones now include what's called the fingerprint sensors. So this fingerprint sensor is mostly fabricated with IGZO. By the way, TFTs are used in order to demonstrate or in order to fabricate or implement the fingerprint sensors. It is also used in flexible screens. Maybe you hear about it when we have some paper like this, and it's folded somehow, and then when you open it like this, then you find a screen. So this is what we call a flexible screen. So Also, TFTs are used in flexible scripts as well. So a lot of applications, but we also have another uh, type of organic of field effect transistors, or for thin film field effect transistors, which are the organic field effect transistors. Organic field effect transistors are very, very promising. They are nominated by the term OFFET. OFFET can be used in various applications. One of the most famous application is the biomedical applications and the wearable electronics. Maybe you hear it somehow in your, if you are tracking some famous American movies or something like that, or maybe if you read about it in the news, whenever you have an electronic devices that can you wear. Or we have also some other uh, applications like what we call the skin electronics, which is the electronics on the skin, or what we call the underskin technologies, whenever you have sensors embedded in your body under your skin. In all these stuff, you need a non-toxic devices which can embed inside the human bodies. Maybe sometimes it's used also in animals or something like that, in order, for example, to sense blood pressure or the glycogen in the blood or whatever its job uh, from the bed in biomedical point of view, but from an electronic model of view, we are seeking for organic materials because simply most of the organic materials are non-toxic material. It can be fabricated at a very low temperature, and sometimes it can be easily fabricated than the organic or than the inorganic material. So this is another broad application for OFACs, which is, by the way, there is some commercial now biosensors which are operating using the OFAC technology. Now, this, well, I'm sorry, this is the end. This is the end of our not only lecture, this is the end of the module dealing with semiconductor devices. It was a 6 lectures, 6 chapters module where we have demonstrated together various semiconductor devices, starting from the foundational devices, such as the PN junction, going through the famous one, which is the most, the BGTs, and then we terminated with what's called some advanced field effect transistor structures. In these advanced field effect transistors, we demonstrated new technologies dealing with field effect transistor, either seeking for a low current, low scale, low voltage application, or for a higher speed by increasing the number of transistors per unit area, follows to Moore's law, or maybe to tackle new applications like the flexible screens, the fingerprint sensors, and also the biosensors application. This is the end of this course. I hope that you have enjoyed this delivery across about maybe 10 weeks of delivery. Good luck in your final exam. Good luck in your next stop. Maybe we can meet again in a new course. Thank you very much and see you later.